explain some of the mysteries of quantum physics and relativity, we need a couple extra steps. As you remember from the first video, which of course you watched very carefully, we need to get some, to define some basic assumptions, postulates or principles, whatever you call them, from which we can derive everything else, all the physics and the physics rules that apply in the physical world. And here we're going to have a look at one of the most fundamental principles that we will use as a basic building block. It's really one of the most important axioms in physics. Why? Well, because it impacts a lot of rules. Actually you can derive a lot of rules in physics from this very basic principle. For instance, you can derive the Newton's laws. Gravity, blah, blah, blah. Maxwell equations, which have been ruling the world of electromagnetic waves since 150 years. Light, radio waves, the Wi-Fi or your mobile phones. Yeah, they work on this. Quantum mechanics is based also from this principle. And Einstein's general relativity can be derived from this principle too. So as you can see, it's a pretty important assumptions and building block. It goes by many names, One of the first names that was used is the principle of least action. Okay, but there is also the principle of stationary action, which is a bit more precise, and then Hamilton's principle, the lazy universe principle. It goes by many names, And of course, we'll use another name. In our case, we'll call it the thrifty universe principle. T-U-P. T-U-P. I like this name. Yeah. Okay. So to define this principle, we have to think a little bit more carefully about what we're talking about here. Physics is about measurements. Okay, there's a few words here that I will use for now without defining them, but that's okay. We'll define them more carefully in a few minutes. But let's assume we understand what that means, And really, physics is about measurements because we will define a lot of concepts in physics using just the measurements. Now, measurements, arguably, in the end, imply movements. It's a very generic thing, but in our case, we'll use, the usual movement thing, change of position over time. And that will be sufficient to understand the 3T universe principle, the T-U-P. And movements of all objects, particles, correspond to an energy called the kinetic energy. And if you wonder what's the link between movement and energy, I can give you an example. Here I have, a nice bottle here. And if I took a ball or a shoe like this, and I give it kinetic energy, Okay, well, as you can see, there is some energy in this kinetic thing in the movement of the shoe, and it does have some impact, and you can feel the energy that was part of this shoe. And this is called the kinetic energy. And the kinetic energy is really the intrinsic energy of the object. It's what's part of it. There's nothing around it that has influence on it. It's really part of the object or the particle itself. Now, there is also another type of energy, which is called the potential energy. And the potential energy represents the influence of the surroundings of your object or particle, So, for instance, in space, you only have the kinetic energy if you let an object go by itself, at a constant speed, linear speed, like this. It will be pure kinetic energy. But if it goes near the Earth, well, all of a sudden, there is potential energy. It starts to change the trajectory, okay? So that's quite interesting. Now, from the kinetic and potential energies, we can derive a very important concept called the action. The action over a period of time corresponds actually to the average value well, actually, it's a sum of all the differences between the kinetic energy and the potential energy. And that's during a period of time, a fixed period of time. It's proportional to the energy and to the time for which you take the action. Okay, so that's a bit abstract. So, let's take an example. So let's assume that you have to go from, point A to point B, which are separated by 100 kilometers on a highway, with your car. And you enter the highway at 8 a.m. and you must be at the exit at 9 a.m. Okay, 1 hour, 100 kilometers. Well, in that case, if there's no problem with traffic, in other words, if there's no potential energy around your car, or things around your car, what you can do to optimize your gas consumption and everything, you'll go at 100 kilometers per hour for the whole time, and that will be the perfect energy saver, ecology, wow. And then if there is traffic, then it's kind of, potential energy that will force you to slow down, and then you will be able to speed up again and then slow down and speed up again and slow down. Well, what you want to do if you want to optimize your gas consumption and the brakes usage, you will brake as little as possible and you will accelerate as little as possible just to make sure that you will arrive at 9 a.m. exactly. And by taking that action, you will really make sure that you'll use as little as possible of gas, and you will not use too much of your brakes. And what's absolutely amazing is that the universe is just like you, or you are like the universe. In other words, whenever there is something to change like that, it will always optimize the way changes are made. And that's actually pretty impressive. So here, what we can say is that TUP, says that whenever the environment of the particle changes, particle, object, whatever, that means that the potential energy will change, and therefore it will compensate with the kinetic energy. And so that the action is as little as possible for the path of an object, the trajectory or the freeway, going from one point to another in a given time, 1 hour in the freeway or highway example. And that's quite amazing, actually. And from that simple principle, we can derive a lot of things, as we'll see. Now, okay, we have defined a simple axiom. Again, if you've watched the first video, we know we have actions. But in fact, to be honest, we've used other concepts in the way we define the TUP. And for instance, we talked about measurements, we talked about space-time, energy, and we have not defined those. And we need to do that. We need to define those. We must follow Einstein's procedures. When he explained times, for instance, to be very careful and define precisely and in an objective way what time was about. And we need to do that too. Actually, we need to be even more precise. Einstein didn't need to be more precise than what he did to explain, for instance, simultaneity, for special relativity. But in our case, since we're talking about, particles, and we'll talk about quantum physics, so we need to be very, very accurate, even more so than Einstein, and that's what we'll do. Now let's start with measurement. Well, we can define a measurement being the assignment of a value to the amplitude, the amount of an observable property. In physics, we call that an observable. And this will be linked to the concept of state, which is very important. So that's also something that we need to define, and we will define in the next video. Now, about space and time, well, measurement is needed to define space and time, just like anything else. And we need to define also a couple of extra steps first. Well, notion of state, we've talked about, and the key notion of simultaneity that Einstein used also to define, to derive special relativity. And so that's what we're going to do in the next slide. This will be our last step before we start to talk about the mysteries and what the answer to those questions are. How exciting.